Think of a river cutting through a canyon landscape. The water flows in a single, unbroken line of motion, never spontaneously skipping over a section of the riverbed. In mathematics, we call this uninterrupted flow continuity. When we map that concept onto a Cartesian plane, continuity has a very specific visual definition. If we analyze a mathematical function, the line should trace smoothly from one side to the other. The simplest test for a continuous function is just that. You can draw the entire curve from start to finish without ever lifting your pen from the page. Zero gaps, zero interruptions. But mathematical systems don't always behave so perfectly. Sometimes a curve stops abruptly. It leaves a physical gap in the grid, and then simply resumes drawing its path on the other side. That empty space is exactly what we need to investigate. This kind of structural failure takes a few distinct forms. It might be a single missing point or hole, a sudden vertical jump between two different values, or a curve that plunges downward infinitely along an asymptote. Whenever one of these breaks occurs, the mathematical rule is absolute. The function is officially classified as discontinuous at that exact x-coordinate. Spotting a broken line is easy enough to do by eye. The challenge is that mathematicians require a rigorous way to document exactly where the system holds together and where it falls apart. To do that, we have to translate these visual interruptions into strict logical notation. We need a precise syntax to map out the surviving, unbroken domains of the function. Let's test our ability to locate these structural failures on a highly fragmented curve. This graph displays a piecewise function that spans across the Cartesian grid. Our specific analysis window for this curve is bounded on the x-axis, starting at -3 and ending at +3. To knot the continuity, we will scan the function from left to right, picking up the trail exactly at our boundary of x equals -3. The path begins smoothly enough, dropping down along a steep, unbroken curve. Then we hit our first structural failure. The curve drops endlessly into an infinite asymptote. This forces a physical break exactly at the coordinate x equals -2. We pick up the path on the other side, tracking the segment as it climbs toward a peak. At the top, we hit a hollow blue circle, a clear hole. The curve jumps downward, creating a second discontinuity at x equals -1. Following this new trajectory, the curve drops down to meet the y-axis, where it abruptly stops at another hollow circle. That is our third break, located at x equals 0. The path resumes below the axis as a straight linear segment, climbing upward until it strikes one final hollow circle. This marks our fourth discontinuity at x equals 2. What we have is a single mathematical system shattered by four distinct breakages at x equals -2, -1, 0, and +2. To properly define the continuity of this entire graph, our next step is to extract those unbroken zones trapped directly between these failure points. We can simplify our analysis by moving away from the full two-dimensional coordinate plane and focusing strictly on the one-dimensional x-axis. This brings us to the concept of an interval. An interval is simply the complete set of all real numbers that exist between two specific endpoint limits, which we can label A and B. If our curve contains holes or breakages at those endpoints, we use an open interval. We visualize this by marking A and B with hollow circles. The written syntax uses parentheses, dictating that we are explicitly excluding those exact boundary coordinates. What if our curve has a solid, continuous start and end? We need a different notation. We call this a closed interval. On our number line, those hollow circles fill in to become solid dots. In text, we represent a closed interval using square brackets, telling us the boundary coordinate is firmly included. Mathematical functions often mix these states. A curve might start with a hole but end on a solid point. We designate this as a semi-open or semi-closed interval, marked by one parenthesis and one bracket. The rule here is strict. Parentheses always mark the exact moments of discontinuity, while brackets denote firm physical inclusion on the graph. By applying these symbols, interval notation acts as a precise algebraic syntax. It turns the visual geometry of a broken curve into readable, logical code. Now let's reverse the process. Can we read this strict interval syntax and use it to draw an accurate graph? This is a blank coordinate grid that we will use to map a new theoretical curve, tracking its path from an x value of -6 up to +6. This specific corridor along the x-axis is our target domain. Our first continuous segment begins exactly at -6, with a solid included point. The line then curves forward, stopping at a hollow, open hole right at -3. Writing the syntax for this piece, we use a closed bracket to anchor that solid start at -6 and an open parentheses to mark the breakage at -3. The graph then jumps vertically. We plot another open hole directly above our last break at -3 and draw our second unbroken curve, stopping at one more open hole at x = 2. Because this segment starts and ends with physical gaps, we use double parentheses. This explicitly traps that unbroken line between two active discontinuities. For the final section, the path jumps vertically again, beginning at an open hole at +2 and drawing continuously until it firmly terminates at a solid dot at x = 6. We document this final stretch with an open parenthesis for the hole at 2 and a closed bracket for the solid finish at 6. If we sequence these statements together, we get a single, complete mathematical string that dictates the exact structure of the piecewise function we just drew. By reading this syntax, anyone can instantly identify the explicit structural failures. The repeating parentheses at -3 and +2 tell us exactly where the curve is broken. Without the ability to use open parentheses, it would be mathematically impossible to accurately describe what happens at those two specific boundary lines. Interval notation provides the definitive map for mathematical functions, offering the specific vocabulary needed to transform visual gaps into precise, logical boundaries.